Here we're going to talk about conductor, which is pretty much ideal metals. So metal conduct electricity. So metal is certainly play a very important role in our daily life and of course electronic devices. So now we'll talk about how the electric field related to interact with metal. Okay, let's get started. Okay, so now basic property, we know material can be categorized mostly into some insulator and conductors. So insulators, like it doesn't conduct electricity. So we know glass, rubber, plastic, that kind of thing doesn't conduct electricity because there's no free moving charges. So charge will conduct electricity or current. Later on, we'll talk about it more. So but because we know material is made of atom, so it has the charge, which cannot move freely, but they are there. So they are called bound charges. So they are bounded right next to the nuclear. So we'll say those are the bound charges. On the other hand, there's another kind of material called conductors, like metal, ionic liquid. Those things can conduct electricity. In other words, there are some free moving charges. So, well, for electron, they are free moving in the conductors. And ionic liquid, they can, the ion can move inside the liquid. So that is the free moving. But of course, there's still some force. We are going to discuss it a little bit later. Okay, so these are called free charges because they are moving freely, doesn't be constrained, like right next to an atom, and the atom doesn't moving in the solid. Okay, so conductor has free charges. Okay, so for perfect conductor is there's no resistance for charge to move around. But in real life, the metal and the liquid, the charge is not that free. It will encounter some resistance, so will lead to resistor. But we are not going to discuss it. We are here to discuss the perfect conductor. So that's it. So it can provide what is the perfect conductor? Just in another way to describe it is that perfect conductor can provide infinite amount of free charges. So of course this is not possible for the real material. Okay. So inside a perfect conductor, this is some rule you should know. The electric field is zero. There's no electric field inside a perfect conductor. Okay. Otherwise, free charge will move, no longer electrostatic. So under the electrostatic condition, there's no field inside a perfect conductor. By placing a conductor in an external electric field, the surface of the conductor will have induced charge, producing internal electric field. Here is EI, internal, and E1 here, sorry, opposite to the external field, and cancel the total field within the conductor, making no charge to move. So that is something important. Second, inside a conductor, there's no free charge. The charge density is zero, no free charge anyway. So that is still the same idea. Since taking the divergence of electric field is this one, so there must be no free charge, no charge density inside the conductor. So no electric field, no charge. If there are charges, they must be on the surface of the conductor. So if there are charge, they must be go all the way to the skin of the conductor. So on the conductor surface. A conductor is an equal potential. So all the potential are the same. Otherwise, charge will move. Okay. So if A and B are 2 points within the conductor, okay, so there maybe must be no electric field. So the potential must be equal. Is the same thing on the surface. So that is the requirement. So electric field is perpendicular to the surface outside the conductor. So if we draw the electric field line, it will be perpendicular to the surface. So it will be perfectly perpendicular. If not, charge will flow. That's it. The charges move to where minimize the total energy. That's the idea. So induced charge. So by placing a positive charge close to the conductor, okay, so we place a charge close to a conductor. So the free moving charge will be attracted by the charge, free charge, the charge you place outside. So it will flow to the surface and where it cannot go outside. So it will be accumulate, will stay on the surface. And also the same sign, the charge with the same sign will go the other way to the other side of the skin of the conductor. That's the idea. So the charge will be put negative charge closer to the and put positive charge further. So just something like this. The conductor will be attract to the charge. So entirely this thing, because it's positive negative, this is positive. So the charge will try to get closer to the free charge. Okay. So these charges are known as induced charge. They are not there if there's no exterior charges. So it only happens when you place a charge here, and this charge distribution happen. So it's called induced charge. They are not there unless you put a charge here. If a conductor is hollow, if there's some empty part of a conductor, okay, and the charge Q is inside. If you place charge inside the hollow hole in the conductor, the outside electric field can enter the cavity. So there's no outside electric field here. Choosing a Gaussian surface enclose the cavity. So we choose a Gaussian surface here. So just cover the cavity. So now we know that in there, we the we know the Gauss law. So the total induced charge at the cavity surface must be negative as this charge. So because we choose it, it must be the enclosed charge. There is no electric field inside the conductor. That's what we said. So this electric field must be zero, And we know we place a charge Q here. So the induced charge on the interior surface of the hole must be the same. Otherwise, it cannot be zero. So that's the thing. So when we put a charge here inside a hole, and the induced charge must be equal to the charge we place it, but in negative, in a different sign. It's a negative. Okay. So here is conductor sphere with irregular internal cavity. So you got a funny shape here. So you place a charge here, but what is the electric field outside the sphere? So still, we can choose the Gaussian surface just as a sphere right outside the conductor. So they'll be trivial. So I leave you to read it. Okay, so now, if a cavity within a conductor without a charge, the electric field must be zero. Okay, so that's also the same thing because inside the conductor it will be zero. So here we just have a loop. We have a loop flowing into the cavity, and the other side is stay in the conductor. So we know there's no electric field here in the conductor. So we know the initial condition and the final condition will decide this integral. So there must be zero inside the cavity. So that's the thing. So if a cavity within a conductor without a charge, the electric field must be zero. So This is some important things. This is called Faraday cage. So that's why there's some performance. You can have some lightning strike, and if you stay inside a metal, uh, here is just a wild cage. So you will be safe because there's no electric field. So you will feel nothing. So that's the thing. That's the Faraday cage. And you can see in many video and even some performance uh, or shows anyway. So surface charge and the force on a conductor. So we always need to consider the force. So electric field inside a conductor is zero. According to boundary condition, electric field right outside a conductor is this one. Okay, so that's some earlier result. So you can go back to take a look at it. And so what we say is inside. If the inside is zero, so the outside, the electric field must be this much. So which proportional to the surface charge density and the pointing outward. Okay, and we say it's normal to the surface. So that checks out. Okay, so the electric field is pointing out. Okay, so electric field right outside is normal to the conductor surface. This is the property we mentioned. Okay, the surface charge density is then we can earlier using the previous result, and the potential has a normal derivative value which is proportional to the surface charge because go back and check the boundary condition things. Okay, so that is the simple proof of it. So we also did it in the boundary condition, but by then we consider the electric field inside and outside. Here only the outside uh, will show here. Okay, so a charge in a field will experience force just like we have. So the force times the surface charge density times the electric field. So that is the force, but remember this is not charge, it's the surface charge density or charge per unit area. So we have earlier, when we have a charge times the electric field is the force. So right now we just write the small f, not the capital F. Means it's kind of density or per unit area. Or unit area is area density anyway. So force per unit area. So we write a smaller f. Consider it's not like a f. It's the force per unit area. Okay. Since the surface charge is on a surface, there are fields on both sides. Okay, so the field on both sides, above and below. So this is actually an average. The electric field is the average of the both side electric field. So the force density, force area density, or force per unit area is the surface charge density, taking the average, multiply the average force on both sides. That's it. So consider a flat surface with surface charge. Okay, so consider there's a thin sheet of charge and with the charge density, surface charge density sigma, like this. Consider only a small patch, just a tiny, here is a circular shape. It has surface charge density, so times the area will be the surface charge. Okay, so the total electric field close to the patch is the total electric field is the electric field contributed by the patch and other part of the surface charge. So there'll be the total electric field. So this force acting on the patch has to be from the other part. So these other things will contribute to an electric field. So the patch will feel the force, just like one cannot act by itself. So the force is whatever exterior acting on this patch. So electric field right above and below the patch should be something like this one. So other is the other things contributed. And here is about electric field and below electric field. So just sum them up together. So the other electric field contributed by other parts is the half of the or the average of the above and below electric field. So that's it. So this average also remove the contribution of the patch itself. Okay, so that is the patch itself we talk about. So this whole for any service charge. Okay, this is something to be aware. Back to the conductor. The field inside the conductor is zero, no field inside. So the average electric field is this one. But we say there's no electric field on the inside of the charge. Okay. So the first force per unit area can be written something like that one. So, well, interestingly, this force per unit area is by definition is pressure. Okay, pressure is the force per unit area. So here we actually have the electrostatic pressure. So interesting. Here the pressure, you just rearrange it. It is proportional to the electric field square. And well, with some constant, as we know before. And well, this you will see quite interesting. Later on, we will talk about it because, uh, yeah, later. Okay, capacitor. Capacitor is somehow very important because you use in the circuitry experiment, and we rely on capacitor to do a lot of electronic things. And it's probably the most common electronic element we use. Capacitor can do a whole lot of things, but now we are just discuss the property of it. So consider two conductors. One have charge Q and the other has negative charge Q. So the total charge is just the volume integral of this part of volume. So that's it. As potential is a constant over the entire conductors, the potential difference between these two conductors is this. Okay, so they have uh yeah the potential since we say the conductor each piece of conductor is equal potential. So the potential here is equal here. And on this other part, the potential here are all the same. So the potential difference can be written down something like this. So uh, that's it. That's the potential difference. But the true charge distribution is different to know. It's difficult to know because the charge will distribute it so very fast and into some steady state and doesn't move anyway. But we don't know the charge distribution. But anyhow, that's it. However, we know the Coulomb's law. We can do things like this to even essentially uh, figure out what is the electric field. If if we double the charge density, even though we don't know the distribution, we still can double it. The electric field will be doubled. So if we have a double 2q and minus 2q, and the electric field is just double, regardless of how it is distributed. So electric field proportional to the charge, proportional to the potential. So if you double the potential will be double. So here we define something. C, capital C is the capacitance. It's the charge divided by the potential difference because they are proportional. So C is the capacitance. That is the important parameter. So by definition, capacitance is determined only by the geometry, the size, shape, and separation of the conductors we mentioned. Capacitance is in the unit of farad, or F, capital F, coulomb per volt. Practical capacitors are very small, tiny, tiny small, commonly in the range of microfarad, nanofarad, even picofarad. So micro is 10 to the minus 6, nano is 10 to the minus 9, pico is 10 to the minus 12. That's it. From time to time, there are single conductor capacitors. From time to time, you will see something like that. The other conductor is considered as the infinitely large sphere surrounding the conductor, carrying same quantity charge with opposite sign. That's the thing. So from time to time, we'll see things like that. Okay, so this example is a parallel plate conductor. Actually, we discussed earlier about two parallel plate which has the same charge. So the electric field inside uh, is is just the electric field, adding the electric field of one single plate and double it because there are two plates. And we say we can superposition the electric field on both sides. And that's one as the example somewhere earlier. Anyway, so two parallel conductor plate. A is much larger than the separation. Okay, this is larger plate, smaller gap, and positive Q and negative Q on each plate. Okay, so the surface charge density is the total charge divided by the area, trivial. Electric field in between is something like this one. This is what earlier we talked about it. So that is the electric field is the charge density divided by the epsilon naught. Okay, or in other words, Q divided by A. So the potential difference is just electric field times the uh, distance. Okay, because of this, the electric field is just uh, the gradients of potential. So that's it. So here is the uniform, so we just divide by the distance or the separation. So that's it. And in that case, we can, by definition, the capacitance is charge divided by the potential difference. So that's it. So this is the parallel plate capacitance. It's proportional to the area. Larger area, larger capacitance. Smaller gap, larger capacitance. That's it. Okay. So example 2.12, capacitor of two concentric spherical metal shell with radius A and B. And well, I'm not go through the detail, but basically you go through and using the fundamental definition and eventually using the charge divided by the potential, you got a capacitor. But still, you can take a look at it. That's the result. To charge the capacitor, we move electrons from one plate to another plate one by one till reaching the charge Q. That's the idea. So that process require we doing work to the charge. So we actually store the energy in the capacitor. So consider at saying some point the charge on the plate are plus Q and minus Q, smaller Q. The potential difference between the plate is, by definition, is something like this. So to move an infinitesimal charge, the tiny bit of charge dq from one plate to another plate, require doing work. So the work done is the potential. So supposedly is we have the potential already, but we need to move a tiny bit. So that is we just rewrite the potential into the charge form here. So the total work done is work and taking just from no charge to the total charge into Q. There'll be something like this. So that is the total work need to be done when we try to make a capacitor with positive Q, capital Q, and minus Q. That is the total energy. So Q is not something we want to worry about because we will use the capacitor to represent the Q. So the half of the capacitance times the V square or the potential square is actually the work we need to do to make the parallel plate to have charge capital Q and negative capital Q. So that's it. So it's the energy stored in the capacitor, which proportional to the capacitance and also proportional to square of the potential in between. Okay. So capacitor, just like I say, is one of the most common one in the electronics and daily life. And there's basically just a different type of power play. So this is one type is you have different play, and you can see some play is connected to this side and the other side is connected to like the second layer is connected to this side. So two sides they are separated and they pretty much add together. So it's like interlocking the plate like that. So you will have effective larger area. Okay, so this is the capacitor in some service mount electronic. And this is more traditional. It is still like two parallel plate, but it rolls up into just a road. And then you connect it and it become pretty much what you see in the lab, electronics lab, which is called electrolyte capacitor. And still many type of capacitors. So you can see it pretty much just like that. This is electrolyte is probably the most common one. And you'll see also ceramic capacitor and tantalum electrolyte. And other a little bit rare to see. Oh, Mylar is probably you see from time to time. Okay, these are the capacitors you can see. All right.